begin today's talk. Our pleasure to have Dr. Daigo here to give us today's Friday seminar on the theoretical physics. The title is about the fluctuation-induced forces in active photonic system. That's very kind.
Thank you. Thank you. Actually, I would like, I thought I would focus on fluctuation-induced forces, but I changed the plan yesterday. And if I finished very quickly this part, and then I will introduce a variety of other topics today. So yeah, let's begin with this first topic on the fluctuation-induced forces. As in the introduction, I'm Daigo. Maybe we have 8 people. I should mute.
Here's one. Why need to mute?
Because there is an echo.
Oh, smart. Okay.
Okay. Okay, thank you. Okay.
Smart. Yeah.
Yes. Okay. So the first part of the presentation is based on those available articles and preprints. This one, okay. These 3 articles, which are already published or available on archive, which are relatively new. And I would focus on this part first. Before going into the details, I would briefly talk about myself. I'm in my 3rd year in the postdoc career. I graduated 3 years ago, and I did the PhD in London with the supervision by Henry, and the study was co-supervised by Professor Kundin at that time. Before the PhD course, I did some experiments, so I think I'm in 6 or 7 years in theoretical studies. So I'm almost a PhD student, but with doctoral degree now. Before the current position in RIKEN, I did the first postdoc in Portugal with Mario, who is one of the collaborators for this first topic. Okay, so I would smoothly in the first topic, which is about fluctuations in active systems, active photonic systems, recently attracting people's attention, like in the metamaterial and metasurface communities, photonic crystal communities, because they are more and more interested in modulation applied from external degrees of freedom, like space-time metamaterials, space-time metasurface are getting popular these days. I took 2 examples, one of which is done by myself and Kun. The other is a work by our ex-colleague. There are various other examples which you can find, for example, in this review article. And I would just bring these 2. For example, if we put modulation, we can mimic the effects caused by active medium, which is physically moving, for example. We can mimic moving dipole, we can mimic moving body. They interact with electromagnetic field, producing, for example, Cherenkov emission and Fresnel-Fizeau drag, which are typical physical effects found in the system which is active. So this is the background, and in this sense, particularly for this type of class of active system, it can be said that it was revisiting electromagnetic effects in moving media. So the contents in the first parts of this presentation is as follows. The first part comprises two examples, which are both related to active photonic system due to motion. The first example, the optical gain produced by constant mechanical motion. So it's a physical motion of a rigid body. And we will see the fluctuation-dissipation relation will be modified in the presence of that motion. And then one of the consequences will be the frictional force, which is induced by fluctuation through the modified fluctuation-dissipation relation. So this is a kind of friction without any physical contact, as we will see. And the second example is related to motion again, but this time the body is not moving, but the carriers inside the body is moving with an electrostatic bias. And then if we apply some interesting structure for that body, like symmetry breaking, crystal structure, and so on, then we may modulate the conductivity tensor of that medium, and then due to the non-equilibrium nature, we may see non-Hermitian effect. In particular, we will see electro-optic effects because we will consider electrostatic bias. So there will be electro-optic effect. And that will again modify the fluctuation effects. And we will see peculiar fluctuation-induced forces. Okay, that's the preview of the contents in the first topic. Let's see the first example, which is an active system, which is realized by constant mechanical motion. The starting point is here. We have a passive slab, which are characterized by a dielectric function, epsilon omega. Since this is passive, they should satisfy this condition. And we will see the effects of motion. Basically, we want to consider the dielectric function in the presence of motion. Let's consider a constant motion. And we want to consider the dielectric response. Intuitively speaking, the response will be considered as follows. For example, if we have incoming electromagnetic field, which oscillate at the frequency of omega, that is observed by that moving plate with a frequency shift. Because of the motion, there will be Doppler shift. So they respond as if the incoming field oscillate at the frequency, which is shifted from the actual frequency. So we can say the dielectric response will be given by the original response with a shift. Theoretically, this can be derived by the Galilean transformation, the limit of the Lorentz transformation at C to infinity. And we can generalize this description by utilizing Lorentz transformation. But for simplicity, we focus on the Galilean limit here. And then we can see an interesting effect here already. Let us check the imaginary part of this response function characterizing this active system. The imaginary part should satisfy some condition. I mean, if we focus on the original response function, this should satisfy that passivity condition. But that passivity condition for the active system will not hold in some spectral region because the imaginary parts, the signature of the imaginary part is determined by the argument, and the argument can be negative. So in this spectral region in particular, the response function, it's negative, it's imaginary, but gives a negative number. So the passivity will be violated in this region. In essence, we will have optical gain in this region. So this is in deep sub-wavelength region. As you can see, this is in this lower triangular region. So this is definitely below the light cone. The slope is defined by the velocity of that motion. So this is in the far below the light cone. And we can say this is in the deep sub-wavelength region. And we cannot, or the propagating electromagnetic field will not see this optical gain because this is far below the light cone. But if we utilize evanescent wave, for example, it may see that optical gain. That's the problem we will consider. So we have this type of setup. And for this example, we will consider force as an observable. To get that observable, we will consider another plate, which is at rest above the moving plate, and calculate the stress tensor on that second plate. That is nothing but the force, unobservable in this system, that will affect it by the optical gain in that region. Okay, so the quantity in question is the stress tensor, particularly the XC component, and we need to take the expectation value because we don't have any inputs, but just fluctuation exists. So we want to take the expectation value, which is evaluated at the surface of the second plate. So we want to know these quantities, the field operators, which characterize the fluctuating field in this system. The field operator should satisfy the Maxwell's equation in the Heisenberg picture. So the Maxwell's equation will be reduced in this case like this because we characterized the response by a single dielectric function. So we will have the dielectric function here, and the permeability is just assumed to be unity for simplicity. We can include making this equation bigger, but for simplicity, again, we will focus on the electric field only here. And the source term appears on the right-hand side, and the current represents the origin of fluctuations in the system. So the field operator will be written in terms of the source current, which represent fluctuations in our system. So we can assign relevant quantity for this source current. And then we can write the field in terms of source current and Green's function, which is basically the inverse of this operator. So the field operator is written in terms of the source current and Green's function. This represents the Hermitian conjugate. And then the quantity in question will be reduced to the current correlation. So maybe you will know that I will talk about fluctuation-dissipation relation because we are interested in current correlation eventually. That will give you the stress tensor. And we can follow, for example, this seminal work by Robb and Welsh to explicitly evaluate this current correlation in terms of the response function. This is nothing but fluctuation-dissipation relation, which are derived by applying the canonical commutation relation, which should hold for electromagnetic field, basically, which can be regarded as a collection of harmonic oscillator, but this is vectorial quantity, so we have slightly modified canonical commutation relation, but this is basically harmonic oscillator. So applying this canonical commutation relation, then we will have this type of relation. And we know that the correlation is related to the response, particularly the imaginary part. Note that we should take the absolute value. If we don't have any optical gain, all the imaginary part in all the spectral region returns positive number. So we can remove optical balls here that reproduce the conventional fluctuation dissipation relation. But now we have the region where we have negative imaginary parts. So that where the vertical bars works. So that will give you additional contribution coming from that spectral region giving optical gain. So we already reduced these angular brackets in terms of the known quantity, because we already gave the dielectric response, and we can explicitly write the response, and we can take the imaginary part and the absolute value. So we already evaluated the current correlation with this relation. So we can reduce the stress tensor in terms of this response function, and we can give the XZ component particularly.
This fluctuation-dissipation theory is called form for some double promise in the gain side. Is there any other assumptions in the
To derive this relation, we need to have all poles, all possible natural frequencies below the real axis in the complex frequency plane.
Yeah.
Otherwise, we cannot have canonical commutation relation. If we have a single pole in the upper half plane, for example, then we cannot have canonical commutation relation for the field operator. So this is the assumption to have this result.
So have an optical gain or have a gain inside. The pose is possible to be in the harmony.
Yeah, it's possible to have that situation, but we can stabilize the optical gain. If the optical gain dominates other dissipation mechanism, one of the poles enter the upper half plane, and then even this modified fluctuation dissipation relation does not work.
So
but as long as the system is stable, all the electromagnetic modes are in the lower half plane. So we have the fluctuation dissipation relation because the system is operating at some stable point, but this fluctuates. That is characterized by this modified fluctuation dissipation relation. If one of the poles enter the upper half plane, as we will see, then all these things break down. Okay. So yeah, this is the point. We will see the breakdown. Okay, this is the force as a function of parameters characterizing this system. The parameters, I'm referring to velocity of the motion and the distance between the two plates. And we can calculate the force, the stress tensor, expectation value of the stress tensor following that modified fluctuation dissipation relation. And we can see the divergence at some point. And this is one interesting result given by the optical gain in the system. Basically, we have increase in the force by increasing the sliding velocity. This is intuitive, but this diverges at some point. This is somehow counterintuitive because the frictional force is not proportional to the velocity, unlike in the conventional friction. It diverges at some point. And it also diverges at some point if we decrease the distance between the two. Well, we can say these divergence will be given by the optical gain, which is easily experienced by the second slab if we get them closer and closer to each other. Or if we provide more gain by making the velocity very large. You can see this is 10% speed of light. So this is impractical, but theoretically we can. And we will see the divergence. And this is exactly what we have in the situation where the fluctuation dissipation, in the situation where we are in the far outside the fluctuation dissipation relation, even outside modified fluctuation dissipation relation. This divergence can be related to the laser type instability. You can imagine we have two mirrors with optical gain on one side, and then this mimics the laser type system because this is cavity with optical gain. So this may experience the laser type instability, intuitively speaking. And this is exactly what we are going to see. We can briefly check the stability of the system by analyzing the characteristic equation for the Fabry-Perot type cavity. This is the reflection coefficient for the upper slab. This is for the lower slab. And then we can check these equations to characterize the natural modes in this system. And we basically solve this equation for omega, and then we get an eigen frequencies which are located in the complex frequency plane. We can check the imaginary part, in particular for the stability condition. And if we have all the poles below the real axis, which can be set like this, then the system is stable. If you remember this type of time dependence of the harmonic oscillator. And we can check how this works in our system. This is various plot for various situations where we change the damping strength for the system. This is one of the straightforward visualization of the system stability. If we have sufficiently enough damping, then all the poles are below the real axis in the complex frequency plane. Then the system is stable. All the eigen modes will be eventually stabilized because of that exponential dependence. But if we have less dissipation in the system, one of the mode may reach the real axis. The corresponding modes have the infinite lifetimes. So the system will face the critical point. Above that critical point, like for example, if we decrease the dissipation mechanism, then many modes enter the upper half plane, then all the theory breaks down. And we were in this regime. We cannot construct the theory in this regime because all these things will break down. So we were focusing on that regime and approaching the threshold from below. This exactly where we had the divergence. This corresponds to that point we have seen in the previous slide. So they are consistent. Okay.
This calculation is quasi-static limit.
Quasi-static limit. Yes. But yeah, I think we will have still the similar results in the even outside the quasi-static limit, as one of the collaborators showed in 2016. Mario analyzed the stability of this type of system previously, and he showed the quasi-static approximation gives a very accurate result, and he confirmed.
The typical in the retardation, the background should be like some slope.
Yeah.
The threshold you can.
Yes. Yes, yes. Okay, so we have seen the system will experience optical gain when one of the bodies comprising system are moving. And this can be equivalent to the electric current inside the body, which is at rest. So as shown by previous studies, we can see an equivalence between these two types of system. The rigid body motion can be mimicked by electric current inside the system. This equivalence has been confirmed in a simple conventional metallic system and graphene systems. So the next focus here is that electric current under the effects of strange conductivity, which is recently reported. In some classes of materials, they show Hall effects without any magnetic field due to symmetry breaking structure inside the material. Basically, this can be seen as an effective magnetic field because this is similar to Hall effect. So the response from the electromagnetic field point of view, this is a plate characterized by response of magneto-optical type. But this is slightly different from the conventional magneto-optical type tensor because of the non-equilibrium nature. In the conventional magneto-optical tensor, we have real quantity if we focus on these coefficients, but this can be complex in the non-equilibrium situation. I omitted the derivation of this response as we are focusing on macroscopic electromagnetism. They showed we will reach this type of response tensor by following the Boltzmann type formalism. They basically calculated the electron conductivity inside low symmetry material that have non-trivial Berry curvature. And then the electric carrier can be follow the skewed path because of the non-trivial Berry curvature. And then we will see this type of response will be obtained. In the diagonal term, in the response, we just have conventional conducting electron response. In the off-diagonal term, we have this cyclotron type response. This is cyclotron type frequency, which is characterized by the effective magnetic field. To give you some intuition, I plot the non-Hermitian part, more precisely skew Hermitian parts of this response tensor. For example, if we focus on the first term, this is just Drude, as we have seen in the previous slide. And then if we turn off the bias, then the second term will give nothing, of course. But if we turn on the bias, then the second term plays a role. Particularly, they show some positive quantity for one of the two circular polarization, while they show negative quantity for the other polarization. So we can say that this one of the polarization will experience optical gain. Again, we have optical gain because this is negative. And this is polarization selective. Okay, again, we are focusing on the force as an observable of this system. Let's consider a different configuration from the first one. Let's say we have a point-like system above that material under the electrostatic bias with the symmetry breaking. And they are characterized by that magneto-optical type response, and we will see the fluctuations around the system by putting probe near this system. For simplicity, I would approximate that probe by a two-level system. And then the force, unobservable in question here, can be given by the gradient of the interaction between that probe and surrounding electromagnetic field. That is written like this. This is just dipole. This is the field operator. If we approximate the probe by the two-level description, then the dipole operator will be given by the transition moment and the 2x2 matrix, the Pauli matrix.
Two-level system means that you have two resonances.
We just have ground states and excited states, single excited states and ground states. So this is just a conventional two-level system. And we can characterize the transition between the ground and excited states by giving these transition moments. So this can be, for example, if we take the hydrogen atom, we can consider 1s and 2s or 1s to p or something. And then we can characterize the transition moments. And if we take the lowest two levels, then we have two-level system. This is a simplified description of an atom. So you can, basically, this is an atom within a very simplified description. We just take the two levels. And we can characterize the transitions by the dipole and Pauli matrices, and the interaction between that probe and field will be written in terms of these scalar products. Where we have the field, this can be written again in terms of Green's functions and the source current. This is what we learned in the previous exam. So we can let us evaluate the angular brackets. The easiest way to evaluate this type of expectation value is to assume the Born-Markov approximation. Basically, we can apply the first-order perturbation theory when we evaluate these angular brackets with several assumptions, Born-Markov assumptions. And then these expectation values will be written like this. We have two contributions. I will give you some intuitive description for this expression. We have two contributions. Here we have the density matrix that characterizes that probe. So we have probe density matrix here, and two process exists here. The first contribution, in the first contribution, we can recognize the raising operator on the most right that acts on the density matrix, which excites the probe. So this can be regarded as an photon absorption process because it excites the two-level system following the annihilation of a single photon surrounding that probe. The second contribution, we have the lowering operator on the far right. So this represents the relaxation of the two-level system and photon emission simultaneously. In both situations, there will be momentum transfer between the field and probe, so we will have force. So we need to count all the process with the weight for each situation. The negative sign here is because of the fact that we have recoiled force when we emit photons, when they emit photons, and so we have negative sign here. So the the question will be these coefficient matrices. They are given in terms of field-field correlations, again, with the derivative here. This can be seen as the momentum of the field, and this characterizes the spectral density in each channel. So basically, this is the momentum of, this characterizes the momentum of the field in each channel. So we can take the all contribution to have the expectation value by calculating, appropriately calculating the density matrix for the probe. Okay, so this is the quantity question. Here I will give some intuition for each coefficient matrix. For the first one, we can observe a peak in the negative y direction. This means the direction which is perpendicular to this bias. We have a peak in the negative y direction. And that peak is in the, that peak gives the negative value. And if we focus on the second term, we have the peak in the positive y direction, but again, this gives a negative quantity. So both of the two peaks gives negative contribution to the force. So they will not destructively contribute to the force, but they constructively contribute to the force because they have the same signature. So the first term was related to the absorption of photons. So the system is more likely to absorb photons propagating in the minus y direction. So it is kicked in the minus y direction. On the other hand, it will emit photons in the plus y direction. So in terms of momentum transfer, it will experience the recoiled force in the minus y direction. So this is consistent with intuition. And if we calculate if we perform the numerical calculation, then we can find they actually feel the negative, the force in the negative y direction. So this is the green curve is the total force in the direction perpendicular to the bias. These blue and orange characterize the two contributions that we have seen in the previous slide. Here are some numbers to produce this figure, which are not impractical compared with the realistic situation. They are not that important here. I would say they are not impractical. Okay, so I would say the take-home message here is the force is in the direction perpendicular to the bias. This is because of the strange conductivity inside the material. So strange conductivity in material can drag electromagnetic fluctuations surrounding them. This is a conclusion. That can be perceived by the probe if we put it near that strange material.
This force is fully due to the symmetry breaking in the low symmetry material.
Yes.
It's not related to the non-linear.
No. This is related to the non-Hermitian effects because we need continuous exchange of momentum between probe and surrounding field. Like, for example, if we have passive system, then eventually the probe will not exchange momentum with the surrounding field eventually. Even this probe is in the excited state at the initial condition, it will emit the energy in the environment, and then it will not return to the probe if the system is passive. Then the probe will not experience any force after all. but we have this type of force even in the steady states. I mean, this force does not depend on the initial states of the probe. The probe will obtain some finite population in the excited states and ground states because we have gain in the environment that will provide energy to the system, that coming from the fact that we are applying bias. And the probe will eventually in some steady states, so it will exchange energy continuously with the system, and associated momentum transfer will be experienced by the probe. So we will have the constant force at the steady states.
Your properties. Can you go back to constitutive relations?
Constitutive relations. Okay.
Gamma here in both epsilon d and epsilon g are equal.
Yes.
What I mean that the gamma in the epsilon d do not play a role. Symmetry. Only the gamma appears in the epsilon g bring the symmetry.
Yes. The symmetry breaking is characterized by this omega 0.
Yes.
Not gamma.
What about the gamma? Yeah.
Mm.
So what I mean that unless if the epsilon g is not equal to is not there, you have the.
Yes.
So, but this one do not to be necessarily non-conditional.
This can be just real quantity, as in the conventional magneto-optical effect.
Used from the materials, for the materials in the.
Yes, but we will not have the constant lateral force if the system is passive. We can have lateral force in a transient situation, but they will not have lateral force after fully relaxed. So
fully comes on the bias.
Yes.
Yeah.
Yes. So the electron propagating inside material will be dragged if we have some effective magnetic field inside the material. Then that skewed path of electrons will drag the electromagnetic field momentum near that material. That eventually affects the fluctuation-induced forces near the material. So
the whole conductance is the whole current is opposite to the force, parallel to the force.
Parallel to the force. Parallel to the force.
So still point to the minus y direction.
Yes.
So the force is parallel to the force.
Yeah. Okay, so I can quickly summarize the fluctuation-induced force parts. We can have optical gain by providing some external energy to the system. That can be given by mechanical motion at a constant speed. That can be mimicked by electric current inside the material. And we can observe the effects of optical gain by, for example, checking the fluctuation-induced forces. In the first situation, we can see frictional force. In the second situation, we can see the forces in the perpendicular direction to the bias. That can be played by the unconventional electronic transport inside the material. So we can observe this type of effects in the macroscopic quantum electrodynamics as well. Okay, so I think I still have several times, so I will briefly introduce several other topics here.
I have some interest in this topic.
Okay. Okay. So yeah, basically I'm interested in the systems with motion, as you found in the previous several slides. And I did some other works in collaboration with other professors. For example, in this study, I considered optomechanical systems with angular degrees of freedom. I would briefly talk about what's the cavity optomechanics and how to make it torsional and show some demonstration. This is a typical toy model of the cavity optomechanics. We have optical cavity here that can be that is movable. And if one of the mirror can move, radiation force can push that mirror from inside the cavity. And then if that mirror wants to return to the original position, then it will affect the modes inside the cavity. So the optical system and mechanical degrees of freedom talk to each other through the radiation force mechanism and the cavity length modulation mechanism. So this is a typical description of cavity optomechanics. If we have increase in the cavity length, then the wavelengths of the modes inside the cavity will increase. That means the frequency of the natural frequency inside the cavity decrease. So the cavity frequency will decrease like this. And this is the displacement of the mirror. So this is the simplest possible description of the quantum optomechanical effects. To make the theory quantum, we just focus on harmonic oscillators describing this system. One harmonic oscillator for optical degrees of freedom, another harmonic oscillator for the mechanical degrees of freedom. And we can focus on the natural frequency of the optical degrees of freedom. As we considered in the previous slide, we have deviation there, and we have the mechanical degrees of freedom coupled with optical degrees of freedom. So this is the typical optomechanical interaction. By adding another term describing harmonic oscillator for the mechanical system, we can fully construct the optomechanical Hamiltonian, which is very simplified description, but in essence, they can capture the behavior of this type of system. The coupling factor is geometry dependent, so we leave it as it is for here. And we can observe this type of interaction where we have three operators. This is typical optomechanical interaction. And in the conventional situation, as we describe, the volume of the cavity changes. In terms of electromagnetic energy, the integration volume changes. So this is eventually give you the optomechanical interaction. In our situation, we want to consider the angular degrees of freedom. So it will not change the cavity volume. So this stays the same. But if the torsion affects the response inside the cavity, if the torsion is perceived by the filling, then the electromagnetic energy can change. So if we want to modulate the system in a torsional way, we definitely need to feel the cavity. And to experience this type of torsion, we need to follow the following arguments. For example, rotationally symmetric response will not perceive the rotation because the rotational symmetry prohibits experiences that action. So we need to definitely break the rotational symmetry inside the cavity. Then we can modulate the response. The simplest possible rotational symmetry breaking is this type of uniaxial response. And then we will have the additional term when we apply twists. And then the electromagnetic energy will be modified like this. This is the original electromagnetic energy. This is the additional one. So when we can apply the conventional quantization procedure by focusing on each modes, which are equivalent to harmonic oscillator. And yeah, the discussion goes like this. We can focus several modes inside the cavity and the effects of torsion. Performing the integration and so on, we will have this type of optomechanical Hamiltonian for our situation. This is the conventional one, which I showed in the beginning. So they're slightly different because they are the same operator, basically. They are operator acting on the same modes, while we have two different operator for two different modes. So they are slightly different in that sense. And so yeah, so we considered the optical parts like that. The two modes contributes. And let's talk a little bit about mechanical parts. If the twist is very small, the twisting angle is very small, that twisting angle will follow elastic wave equation. That is nothing but conventional wave equation at the lowest order. So it can be quantized as in the case of electromagnetic field. So this is just a harmonic oscillator. This can be seen as a single boson. So eventually we will reach this quantum mechanical description of the situation where we have a twist and optical modes. So this is the summary of the interaction Hamiltonian. And once we have a Hamiltonian, we can calculate linear response, which is straightforward. Following the, for example, Kubo theory, we can calculate the response. For example, we can calculate the amplitude of this torsional oscillation under the driving laser by applying the linear response theory. And we observe two peaks, for example. One peak is at the mechanical eigenfrequency. The other peak is at the difference in the frequency between the two optical modes inside the cavity. So they act like this. Indeed, this laser drive acts on the mechanical oscillation in the angular direction if we have rotational symmetry breaking inside the cavity.
Not like fluctuation.
We have, and this is just the intensity of the mechanical oscillation. So it's like expectation value of E times E.
Yeah.
But it's in the mechanical degrees of freedom. So this is also fluctuation, the force coming from mechanical fluctuation in the angular direction. That fluctuation is described by a single bosonic operator in the model.
You have the torsion.
Yes.
The torsional motion will be coupled with cavity mode.
If we fill the cavity with material which shows uniaxial response.
Yes.
Yes.
Then you calculate the interaction by G terms.
Yes. Yes. Yes.
And then the G will modulate both the cavity mode and the torsional motion.
Yes.
But in this plot, you only plot you're shining a light.
Yes.
And then what quantity you are trying to calculate? Okay, because in previous scenario, there's no internal light. It's only a cavity mode. Torsional plate.
Mm.
And you calculate the coupling between them. Have some both the cavity mode and this one will be changed. And the motion will be changed. What's in this plot? You're shining a light on it.
Yes.
Yes, I think the whole thing changed. Because in previous analysis, you do not assume these thermal.
No.
Yeah.
But with some gain provided in a mechanical way. For example, in the first scenario, friction, we move one of the plates. That will give energy to the system, which is dissipated and resulting the friction. The second scenario, we apply the electric bias that talk to the other system, which is probe. It experiences force. In this situation, we put light on the system, and we don't put any mechanical action on the system. So the optical degrees of freedom will talk to mechanical degrees of freedom through the optomechanical things.
So we just shine light the fiber top.
Yes. Yes. So different type of driving mechanism has been considered so far. The mechanical, electrostatic, and optical. Okay, so this will be summary. This was published several years ago in PRA. So you can check the details here. And maybe I should stop here or okay, then I'll move to the other one, which is about the transfer of spin degrees of freedom between two systems, again induced by motion. So everything is related to motion here, in some sense. For these parts, the two articles were published. One is in the 2022, the other is 2024. Both of them are related to this presentation. There are three key ingredients. We have tunneling transport. We will see tunneling transports and spin degrees of freedom, and they are intertwined to give you spin transfer between the two contributors. And we will consider mechanical motion driving the transport. So the question will be, a motion can drive the spin transport. And I will briefly discuss the effects of velocity, temperature, spectral broadening, and so on. Now, tunneling transport is a ubiquitous non-equilibrium phenomenon, which can be discussed with this type of exchange type interaction. For example, we can consider two terminals and electron hopping between the two. This type of mechanism appears in many situations, for example, scanning tunneling microscopy, superconducting tunneling junctions. Even in the photonic situation, we can see the tunneling type phenomena. All of these situations can be described by this type of Hamiltonian. And similarly, we can consider the tunneling of spin degrees of freedom by similar Hamiltonian. They can exchange spins, as in the case of the Heisenberg model, for example. And this is the focus of this part. People considered various mechanisms to utilize this spin tunneling type coupling. For example, people can apply microwave irradiation, make one of the two terminals non-equilibrium states, and then there will be population imbalance between the two terminals. That eventually leads to the spin transport between the two through this coupling. If we heat up one of the two terminals, there will be Zwick-like interaction, Zwick type effects. And again, we can see the transfer of the spin degrees of freedom. They are already confirmed in experiments, and people can also accumulate electron spins on one of the two terminals that will be perceived by the other terminal if we make them closer enough to each other. This was also demonstrated long ago. So microwave temperature, this can be done by applying electrostatic bias with spin orbit interaction. And the question I would pose is that the following: mechanical motion can drive spin transport or not. This is similar to the situation we considered in the very beginning, non-contact friction. So these are studies which are related to non-contact friction. They are a Casimir-related mechanism. They are electrostatic mechanism. Anyway, we can have non-contact interaction between the two systems in the motion, as we have seen in the very beginning. So I thought this can be regarded as tunneling type problem. If we simplify the situation, we transfer momentum from one side to the other side. That will lead to the force on the other side. That is nothing but what we considered in the first part. A similar scenario can be considered with two magnets. For example, if we prepare two ferromagnetic insulator, they can be easily described by Magnon degrees of freedom. So we can use analogy between quantum optics and magnonics at the lowest order. And only key here is the interaction of the exchange type. And the mechanism to drive the transport is mechanical here. So the quantity in question is the density of spin, which is evaluated by analyzing magnonic degrees of freedom in this situation. In particular, we are interested in the rate of change in the spin accumulation. That can be discussed easily in the reciprocal space rather than in the real space for this type of symmetric, translationally symmetric situation. It is more easier to work in the reciprocal space. And the quantity in question here is the rate of change in spin density. By utilizing the Heisenberg relation, we can rewrite the derivative in terms of the commutation relation, and we would like to evaluate the angular brackets. So we need to evaluate the angular brackets in the non-equilibrium situation, as we have done in the very beginning. Can we do that for this type of magnonic system? That's the question. So this is the quantity in question. I think I need a lot of times to describe this formalism, so I would skip the details, but thanks to this Keldysh formalism, we can evaluate the angular brackets far from the equilibrium situation, which is similar to Kubo formalism, but for non-equilibrium situation. And then we have this type of expression, which can be intuitively understood. We have tunneling strengths, we have overlap in the spectral region, and we have population difference. And we need to integrate all the contribution over all possible modes and frequencies. That will give you the amount of spin transferred between the two terminals in the presence of motion. So the question is how the effects of motion enters the expression. As we have seen, this enters the expression in the form of Doppler shift, as we have seen in the very beginning. So we can utilize the Doppler shifted susceptibility for magnonic systems. And then we can use just conventional susceptibility for the other insulator, whose fundamental modes are described by a single magnetic modes. And we can just use Bose distribution function just because they are just bosons at the lowest order. And yeah, the population is slightly shifted due to the motion. This can be regarded as a momentum dependent chemical potential. So the chemical potential difference will give you transport between the two magnetic insulators. This is the spectral overlap. This is the population difference, and we can see the population difference occurs on one side in the reciprocal space. We can multiply these two to have finite amount of spin transfer between the two. If this is symmetric, after multiplying these two, everything will be cancelled after integration, but this is slightly asymmetric, let's say this is asymmetric. And then we will have finite amount of spin transfer between the two. That's the intuitive discussion of the things. We can study the velocity dependence and temperature dependence. If we increase the temperature, we have more spin transport between, let's say we have more magnon transport between the two magnets. Because higher temperature, we have more magnons thermally activated, which can be transferred through the interaction Hamiltonian. And if we increase the velocity, we have more chemical potential, so more spin transport occurs. These are typical parameters for YIG, and so basically this is not in practical.
Only one polarization, just up and down.
Yes, just two, yes.
Also, the spin turning.
Yep.
Only one spin.
In this scenario, we are considering finite magnetic field to align the spin magnetic moments.
Okay, so you have one spin.
Yes, and then they can fluctuate. And this is nothing but magnon. And we have two magnons on opposite sides. And then they can talk to each other.
Okay, two YIG.
Yes.
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 By magnetic.
Yes.
The spin current will be.
Yes. Yes. Okay. Yeah, this is the temperature dependence. This behaves almost linearly because the distribution function behaves linearly at the high temperature. There's a room temperature, and in the low temperature, we have nonlinear dependence on the temperature, but almost it behaves linearly. And if we increase, for example, if we prepare dirty magnets, then the magnon have shorter lifetime, then it will have broadening in the spectral region. So we can discuss that effects in this simplified framework. If the magnon has a very sharp peak, then there will be no spin transfer. They cannot talk to each other because they are too sharp and no overlapping in the spectral region. So we need definitely finite broadening. And we will also spoil the transfer if it is too dirty. This is very intuitive. So in both situations, we have zero spin transport. So we have optimal condition between the two extreme limits. And this is the curve describing the effects of broadening, the dirtiness. Okay, so this is the conclusion for that part. The constant motion can activate spin transport between the two magnets, basically magnon transport. We can generalize this for more general systems by replacing magnon operator by spin operator. We can study the response in this non-equilibrium situation by applying Keldysh formalism, which I skipped here though. And we can study the parameter dependencies. And they are presented in these articles. I did not update this one. Okay.
You can have 7 minutes to finish it now.
Okay, then I will enter the final parts, which were the topics I worked with Kun in for my PhD research. So this part are based on 3 articles which we published together before. Okay, again, we're going to consider moving systems, and as I've introduced in the very beginning, we will see Cherenkov-type effects, and similarly to the first topic, we will see frictional force here again. So this is meta surfaces which are structured in space. As I mentioned in the very beginning, we can structure the meta surface in time. So they demonstrated in the microwave configurations. Most of the studies were focusing on the light scattering, asymmetric scattering, and non-reciprocal reflection, and so on. And I wanted to discuss the physics more, like power consumption by applying the modulation, or is there any frictional force associated with that power consumption, and so on. I wanted to discuss this type of physics-related problem rather than just electromagnetic simulation or analytical calculation. So this will be the topics covered in this part. I would focus on the modulation of a very simple type, which looks like a traveling wave. And I will just introduce briefly how to analyze the scattering by that system, which looks like moving. And we will see emission of field from the moving types, synthetically moving type system, and they will consume energies, electromagnetic energies, and there will be associated radiation force. So this will be the situation we would like to consider eventually. We will have meta surface which looks like moving, but it's not moving physically. It just appears moving. And the question will be, can it emit radiation? Can it consume electromagnetic energy? Can it affect other contributors in the sense of force? These would be the quantity in questions: power consumption, force, so in the surrounding area. So the first things to do is characterize the surface, which looks like moving. This can be modeled by, for example, corrugation, which is moving like elastic wave. And we can reduce it to, we can compress it in a very thin region if we want to make the theory effective. So this is the starting point. We have a single interface which is very flat. We can consider the textbook problem, the reflection and transmission at this flat interface. We will expand the waves in a plane wave basis in this situation, and we match the boundary condition at this point. This is textbook problem. And we will see the reflection and transmission coefficients from that simultaneous equation. The way we can deal with this corrugated surface is similar. We can find the eigenmodes in this system, expanding the field on the basis of the eigenmodes, and impose the boundary conditions. For this part, And that part, we have just plane wave basis. And if we focus on this region, this is periodic. So the eigenfunction becomes Bloch type. So we can impose the boundary condition between these two parts and these two parts to have reflection and transmission coefficients for this corrugated system. Or we can utilize Green's function if we proceed perturbatively. We can start from this single interface, which is very flat, and we can introduce corrugation on the flat interface that can be regarded as impurities. And the calculation can be based on the Green's function. We can calculate the scattering from impurities perturbatively using Green's function. And we can move on to the moving corrugation. But we will face several difficulties. For example, eigenmode analysis, well, it becomes not that simple because of that time dependence. And for the Green's function approach, we need to evaluate Green's function in the time domain, which is typically requires high computational power if we want to proceed numerically. And we cannot, it's difficult to proceed analytically as well because we have two arguments instead of one argument in the frequency domain. So I wanted to construct alternative approach. I wanted to apply alternative formalism for the system which is moving. And we can match directly the boundary, the quantities at that moving and curved interface by utilizing the basics of the differential geometry. I was inspired by this old paper where they considered multiple corrugations and they utilized basic differential geometry for calculating this type of systems scattering light. And that was static boundary. So I wanted to make it for moving, but the procedure is, let's say, straightforward. We can evaluate the tangential vector on that moving interface that is space-time dependent. And we can utilize the conventional plane wave expansion by splitting the system into two parts by this curved and moving line. Over that curved and moving line, we have homogeneous system. Below, we have homogeneous system as well. So we can utilize the plane wave expansion for these incident, reflected, and transmitted fields. And the question will be matching the boundary condition. We can do that by utilizing the space-time dependent tangential vectors and the profiles of the interface. So we need to solve this type of simultaneous equations. And if this modulation is periodic, we can simplify these equation systems by applying Bloch type formalism. Basically, we apply the Fourier transformation, and then the continuous decrease of freedom becomes discrete decrease of freedom, and the problem is reduced to solving the simultaneous equation. The intuitive understanding of the simultaneous equation is like this. We have incident wave and we have reflected waves. Due to the structure on the interface, we will have diffraction, and due to the motion, the frequency will be shifted as well. And many higher order diffractions exist here. And we can collect all the modal amplitude in a single column vectors, which are nothing but the quantities appearing in these simultaneous equations. And the input wave vector is characterized by a collection of quantity with just one finite element. So these are the quantity, and the information of the geometry and the motion will be encoded here. So this is the equation we need to solve for that system. And we can calculate the relationship between the input and reflected input and transmitted. They are nothing but transmission and reflection coefficients. We can consider a very simplified situation. For example, we can take the electrostatic limit and uniform limit. Basically, we will take omega k parallel to 0, and then we have just input, which is static and uniform. And we can calculate the reflected and transmitted field, which is the field generated by the modulation under the applied bias, which is static and uniform. So basically, the interface will emit fields. For example, in this situation, which is the interface, which is slowly moving. So this is almost the same as the electrostatic problem of a grating. We will have the charge distribution over the structured interface because we have permittivity difference between the two. And that difference in the distribution of charge will follow the motion of the interface, the synthetic motion of the interface. And we can change the parameter to mimic a very fast motion of the interface. This is not moving, but it's synthetically moving. And once that synthetic motion exceeds the Cherenkov condition for the medium, we will see the Cherenkov type pattern inside the medium. The Cherenkov type, this is a series of Cherenkov type pattern inside the medium. Above the interface, we have just a vacuum condition, so we don't have any emission here, and we have emission inside the medium. When we exceed the velocity of light in the medium, we will have emission of Cherenkov type radiation. And we can further increase the speed of the synthetic motion because this is synthetic. We can exceed the velocity of light even in the vacuum. So we will see the Cherenkov type pattern even in the vacuum. So this is the consequence of the modulation with the electrostatic bias. We now know there will be Cherenkov type emission from the synthetically moving metasurface, and that could affect the other side if we put something. And there should be a force which is related to the electromagnetic power loss on that synthetically moving material. First, power consumption. I mean, for this part, we already calculated the field distribution as you have seen in the previous slides. We can calculate this one. And then this is again given by the products of the two field components. So now we can calculate these quantities. And we focus on the power consumption first, the power loss. And this is the plot where the horizontal axis represents the decrease of modulation in the spatial direction. The vertical axis represents the modulation frequency in the time direction. If we increase the speed of modulation in time, we will have more electromagnetic power loss. If we cut this diagram here, we can see this type of pattern. This is basically light cone. And inside the light cone, we will have Cherenkov type emission, while outside the light cone, we have no emission. So very small power consumption because electromagnetic energy cannot escape the metasurface in that region far from the light cone. And this is the force related to the emission of radiation, which is Cherenkov type. That is singular around the edge of light cone. If we cut here, we can see this type of singular plots where we have sharp peaks at the right edge of the light cone. The direction of the force will be dependent on the direction of the modulation in space. So we have opposite signs. Basically, they will provide momentum in the opposite direction. Okay, so this finally concludes the presentation. We have synthetically moving metal surfaces that can emit electromagnetic waves, which is Cherenkov-like after exceeding some Cherenkov type condition. So we can we can evaluate the amount of radiated power and the force associated with that emission. Okay, this finished the talks. Thank you very much for your attention.
Okay. I have several questions for the spin injection part. The formula you come from Kaddish.
Yes. Yes.
Kaddish formula you evaluate the non-equivalent response.
Yes.
But what you put down is still within the perturbation.
Yes. Yes.
Frictional.
Yes. Kaddish works only for the perturbative situation.
Yeah.
It is impossible to work with the non-equilibrium situation. Basically, the formalism reduced the problem to the equilibrium situation by perturbatively changing the equilibrium situation to the non-equilibrium situation. So it is difficult to. Basically, we use Green's function, so we cannot.
Green's function, not Green's function.
It's Green's function.
Yes.
So it's very difficult to go beyond the perturbative regime as long as we work on this Green's function type formalism. So this is still in the perturbative regime.
Maybe a interesting question.
Mm.
The formula is, the Kaddish formula is quite similar. It's not the Kubo formula, correct? Of course, but can we treat it as a generalized linear response, a generalized Kubo formula in non-equilibrium?
Yeah, it's a slightly generalized version of the Kubo formula. So it's almost the same, but in the case of Kubo formula, we can just focus on the retarded or advanced Green's function.
Yes.
In the Kaddish situation, we need to deal with 4 Green's function, retarded, advanced, lesser, and greater, or we can reduce it to 3, retarded, advanced, Kaddish.
Yes.
So the formalism looks like very similar to the Kubo formula, formalism, but the Green's function becomes a matrix.
Yes.
So they are the same, but in symbolically they are the same, but in the Kaddish situation, Green's function becomes a matrix.
In this situation, Kaddish can handle this temperature of the two are different.
Yes, yes, yes.
2 different temperatures.
Yes, because in the Kaddish formalism, we can disentangle the 2 bodies to the equilibrium situation. The Kaddish can decouple the 2 by going back in time. So they are prepared in equilibrium situation and perturbatively interacting. And they start interaction perturbatively in time, and they will reach the steady states. And then that situation can be analyzed perturbatively with the Kaddish formalism. The problem is reduced to the equilibrium situation, local equilibrium situations.
And for the torque part, and you have a rotation.
Mm-hmm.
Can you calculate the 2 forces, lateral forces, go torque and R process? You have a torque in the Z direction.
Yes.
The notation will be not.
Yeah, in this direction.
Yes. So there should be 2 forces in play.
Yes, yes.
Can you calculate the change in the spring constant or the initial momentum?
What I calculated here
Yeah.
is the change in the angular momentum
Yes.
in the elastic degrees of freedom. That is equivalent to the torque applied to the elastic body. So technically, I didn't calculate the force. I calculated the change in the angular momentum. But it
Calculate the change in the initial momentum or in the spring constant.
the spring constant is fixed, which is given by the material property of
So
the
you do not-
elastic body. Yes, if we were in the highly nonlinear situation,
Yes.
the spring constant changes, of course. That will give you nonlinear optomechanical interaction.
Then, for this kind of modulation, it's called an optical spring effect.
Yeah.
For spring constant, can you change?
Yeah.
Spring constant.
Yeah, the spring itself is there, but if we put optical degrees of freedom,
Do not consider the change to the spring constant by the vacuum fluctuation in the jacket.
we can say in that way. We can say in that way due to the coupling between the elastic body and the fluctuations in the quantum optical degrees of freedom, the elastic constant may experience, let's say, renormalization. That's the one way to see the interaction between the twisting mechanical motion and the fluctuations in the electromagnetic fields.
What's the typical G value you put down in the formula?
Well, that's highly dependent on the geometry. For this situation, I used the number for quartz, which is very small, like in a micro size. And we can calculate the spring constant for that quartz micro cavity or some beam. Okay. Maybe very basic question will be very fine. I talked very quickly around the end of this presentation, so and I covered a variety of topics. So basic questions are quite welcome.
I think we can discuss.
Okay,
Okay, then I'll send it out again.
thank you.
大夫，那个你，你